Here's a challenge. I hand you a 3x3 matrix A and ask you to compute A to the 100th power. Brute force means 99 matrix multiplications with the entries ballooning at every step. But if I tell you that A's eigenvalues are 0.9, 0.5, and 0.1, I can tell you right now, A to the 100th is essentially the zero matrix. That's the power of diagonalization. To see why, let's start by thinking about A squared. First, recall the diagonalization itself. If A has n independent eigenvectors, we can factor A as S times lambda times S inverse. Here, S holds the eigenvectors as its columns. Lambda is the diagonal matrix whose entries are the eigenvalues. This factorization decouples A into three clean pieces: a fixed change of basis given by S, a pure scaling given by lambda, and the inverse change of basis, S inverse. That structure is exactly what makes taking powers of A trivial. Here's the eigenvector argument. Start from AX equals lambda x. Now apply A one more time to both sides. A squared times x equals A times lambda x. Since lambda is just a number, we can pull it out front, giving lambda times AX. But AX is lambda x again, so this becomes lambda times lambda x, which is lambda squared x. Same eigenvector, the eigenvalue just got squared. So A squared has the identical eigenvectors to A, with eigenvalues lambda 1 squared, lambda 2 squared, and so on. Powers of A inherit the eigenvectors and only act on the eigenvalues. Now for the algebraic argument, a squared equals S lambda S inverse times S lambda S inverse. Look carefully at the middle of this product. We have S inverse times S sitting right next to each other, and that collapses to the identity matrix. So the expression becomes S lambda times the identity times lambda S inverse. The identity does nothing, so the two lambdas merge, and we're left with S lambda squared S inverse. The outer S and S inverse survive, the inner pair annihilates, and all the action is concentrated in lambda squared, which simply squares each diagonal entry. Matrix exponentiation has been reduced to scalar exponentiation. The pattern generalizes beautifully. A to the k equals S times lambda to the k times S inverse. When you multiply A by itself k times, every interior S inverse times S collapses to the identity, leaving just k copies of lambda fused together into lambda to the k. And the lambda to the k is trivial to compute because it's a diagonal matrix with entries lambda 1 to the k, lambda 2 to the k, all the way through lambda n to the k. Let's see this in action. Start with lambda equal to the diagonal matrix with entries 0.9 and 0.5. Now raise it to the 10th power, and you get 0.349 and 0.000977. Raise it to the 100th power, and you get roughly 2.66 times 10 to the minus 5 and 7.9 times 10 to the minus 31. Each eigenvalue just shrinks independently. Contrast this with LU decomposition, which offers zero leverage for computing powers. Diagonalization is built exactly for this job. Now the big question, what happens as k gets huge? Here is the stability theorem. To the k approaches the zero matrix if and only if every eigenvalue has absolute value less than 1, every single one. Right? The reason is structural. S and S inverse are fixed finite matrices. They cannot rescue you. All the dynamics live inside lambda to the k. If even one eigenvalue refuses to shrink, that diagonal entry survives and A to the k does not vanish. Why do we use absolute value and not just lambda itself? Right? Because eigenvalues can be negative or even complex numbers. Right? Take lambda equals negative 0.9. This still decays because its magnitude is 0.9, and 0.9 raised to the k goes to 0. Now take lambda equals 2i. This blows up because its magnitude is 2, and the 2 to the k goes to infinity. What really matters is distance from the origin in the complex plane. So draw the unit circle. Every eigenvalue strictly inside the circle means decay. Anything on the circle or outside means trouble. Right? Magnitude exactly equal to 1 is the knife's edge. Right? The powers stay bounded and may oscillate, but they do not decay to 0. Let's watch two cases side by side. Case 1, the stable case. Lambda equals the diagonal matrix with entries 0.9 and 0.5. Raising it to the 10th power gives the diagonal with 0.349 and about 0.001. By the 100th power, both entries are essentially 0, roughly 2.7 times 10 to the minus 5, and 7.9 times 10 to the minus 31. Dramatic decay, a to the k goes to 0. Now case 2, the unstable case. Lambda equals the diagonal matrix with entries 1.1 and 0.5. That 0.5 still dies out just like before. But 1.1 raised to the 100th power is about 13,780. One rebellious eigenvalue hijacks the entire matrix. A to the k diverges, despite having a perfectly well-behaved companion eigenvalue sitting right next to it. Two warnings before we move on. First, a to the k does not mean squaring each entry of a. Entry-wise powers are a completely different, unrelated operation. Matrix powers mean repeated matrix multiplication, and the diagonalization is what exposes the hidden scalar structure underneath. Second, magnitude exactly equal to 1 does not mean stable, it means bounded. A to the k neither explodes nor dies away, it persists or it rotates forever. That knife's edge behavior shows up in pure oscillators and in undamped physical systems. This tiny condition, a circle of radius 1, governs an enormous chunk of applied mass, discrete dynamical systems, Markov chains, iterative linear solvers, numerical stability, population models, page rank, economic equilibria. Any process driven by repeated application of a linear map lives or dies by its eigenvalue magnitudes. Diagonalization turns the 100 matrix nightmare into 3 cheap operations, and it turns long-term behavior into a single glance at the complex plane. The eigenvalues are the crystal ball. The unit circle is the boundary between stability and chaos.